This presentation is on the continuation phase of internal erosion. Over the following slides, these are the learning objectives that we'd like to meet. We're going to explain the continuation phase of internal erosion, assess existing filters for particle retention and likelihood of continuation, identify conditions that may adversely affect filter performance, and assess constricted or non-erodible exits for particle retention and the likelihood of continuation. We'll begin the presentation with an overview of the continuation phase of internal erosion. Then we'll move on to a discussion of how to assess existing filters and discuss other filter considerations that can affect filter performance. We'll wrap up with a discussion of more and less likely factors, as well as constricted or non-erodible exits that may be associated with defects in embedded structures. With that, we'll move on to our first topic of discussion, an overview of the internal erosion phase of continuation. Continuation is the second phase of internal erosion. Once erosion is initiated, it will continue unless the eroding forces are reduced or the passage of the eroded particles is impeded in some way. Thus, erosion may be interrupted or arrested by filtering action in downstream materials in the embankment or foundation. Dam engineers have known since the 1950s and 1960s that the most efficient way of stopping the erosion process is to zone the dam and to provide filters. Terzaghi is generally credited with the development of modern filter criteria, but Sherrard in 1984 conducted a laboratory study adding base soil categories and regrading to the procedure. If the D85 of the base soil is the same size as the effective pore diameter of the filter, then the D15 of the filter equals 9 times the D85 of the base. This criterion applies to base soil category 1, which are soils with fines contents greater than 85%. There are two fundamental functions of filters. Particle retention is the focus of this presentation as a defensive measure against internal erosion, while the other function of filters is permeability. Criteria for permeability vary between the federal agencies, but all of them compare the D15 of the filter to the D15 of the base. Filters are designed to prevent particle movement from intergranular seepage flow where defects are present in a base soil or seepage water flows through pore spaces of a soil mass in an embankment or foundation. A properly designed filter prevents movement of base soils by seepage forces at a discharge face. The filter supports the discharge face such that bridging between closely spaced contact points prevents any movement of base soil particles into the filter. The filter is also sufficiently coarse to allow seepage water to escape freely. The next few slides illustrate the details of filter action. Eroding soil in the crack is caught at the filter face, stopping flow in the crack. High gradients cause hydraulic fracturing from the crack to the adjacent filter. That hydraulic fracturing from high gradients between the water in the crack and the adjacent filter causes some widening of the filter cake near the crack. The high gradients cause further widening of the filter cake until the gradient is ultimately reduced. The filter cake, having a very low permeability, covers the width of the crack and some distance on each side of the crack. The remaining filter is open for collecting seepage flow through the pores of the soil between cracks. Dam zoning can be grouped based on their capability of providing control for internal erosion in the embankment. This is based on the provision for or lack of filters and statistics of failure and incidents in Foster et al. 2000. It does not take account of details of dam zoning, design, and construction, and therefore it's only a general guide. When evaluating continuation, three types of exit conditions are generally considered. An unfiltered exit is a free or open face. An inadequately filtered exit may still provide adequate defense even if it doesn't meet modern filter design criteria. This requires an evaluation of the base filter compatibility for particle retention that we're going to discuss later. The last exit condition is a constricted exit, where the internal erosion occurs through a non-erodible open defect in a through penetrating structure or rock foundation. This figure shows examples of various open or unfiltered exits in the foundation. It includes a potentially inadequate foundation filter at the base of the dam, the sand layer daylighting on the downstream side, the sand layer eroding into an open work gravel layer that daylights downstream of the dam, and the sand layer eroding into open joints in the bedrock that daylight downstream of the embankment. Now that we've covered an overview of continuation, we move on to a discussion of how to assess existing filters. Many existing dams have filter or transition zones that are coarser than required by modern filter criteria. Foster and Fell in 2001 conducted additional research with an emphasis on dispersive soils and additional erosion boundaries to help answer the questions of if a concentrated leak develops through a core, will a filter or transition zone prevent continuing erosion? How much erosion is required for self-filtering to occur? And can this amount of erosion be tolerated? The concept of regrading the base soil was developed by Sherrard to account for broadly graded soils. Broadly graded soils can be internally unstable and have inadequate particle retention, and regrading corrects for this phenomenon. Permitting the inclusion of gravel within the base soil gradation will lead to a large D85 of the base and subsequently a large D15 of the filter. Since gravel particles don't have any particle retention capability in broadly graded or gap graded soils, the resulting filter gradation will be too coarse to provide particle retention of the finer fraction of the base soil. Regrading is performed on the number 4 sieve so that the maximum particle size of the regraded base soil is 4.75 millimeters. During the regrading process, a correction factor is calculated by dividing 100 by the percentage passing the number 4 sieve. The correction factor is multiplied by the percentage passing of each sieve size of the base soil smaller than the number 4 sieve, with the new values of percent passing being the regraded base soil. This logic diagram is used to determine which base soils require regrading and the operation used to achieve the regrading. When the soil does not contain any gravel or particles larger than the number 4 sieve, regrading is not required. If the soil does contain gravel, it still may not require regrading if it meets all 3 properties listed. If one or more of the properties are not met, the soil should be regraded using the procedure shown. If the maximum particle size is larger than 4.75 millimeters, or the number 4 sieve, then you regrade so that the maximum size is 4.75 millimeters. If the base soil is gap graded, it must be regraded on the closest sieve to the particle size that is missing. Fell et al. 2024 recommends selecting representative coarse, average, and fine gradations of the original or regraded, if applicable, base soil. For example, if the representative coarse gradation is indicative of the coarser 5% of the base soil gradation envelope, and the representative fine gradation is indicative of the finer 5% of the base soil gradation envelope, the representative average gradation is indicative of 90% of the base soil gradation envelope. The no erosion filter test was developed by Sherrard and Dunnigan to determine the ratio of D15 of the filter and D85 of the base that establishes a no erosion condition for non-dispersive base soils. Additional research by Foster and Fell informed the development of the no erosion condition for dispersive base soils. Particle retention criteria for modern filter design is based on the no erosion filter concept. Foster and Fell also developed a device to evaluate the potential for continuing erosion by modifying the no erosion filter test. To evaluate continuing erosion, they re-ran the no erosion filter test with a coarser filter. After the test, the water passing through the filter was collected and the eroded materials were dried and weighed to determine the loss of the base soil that was required to seal the filter. To ensure that continuing erosion was taking place, they also used thicker base soil specimens to allow for greater erosion losses. This process was repeated with progressively coarser filters until the filter was not sealed. Based on observed eroded materials from the continuing erosion filter tests, erosion conditions were established depending on the ratio of particle and pore sizes. Thus, erosion will either not continue, no erosion, stop after only minor erosion, some erosion, or stop only after a significant amount of erosion, excessive erosion, or erosion will continue, continuing erosion. These erosion conditions were derived from continuing erosion filter tests using very high water pressures and a preformed hole, so therefore the results are likely conservative. The following slides discuss these 4 erosion boundaries in more detail. For the no erosion condition, the filter is finer than the no erosion boundary and seals with no or practically no erosion of the base material. When evaluating an existing filter, start by performing an initial screening using the no erosion design criteria. Modern filter criteria used by Reclamation and USACE are adopted from FEMA 2011. The D15 of the filter is compared to the D85 of the base for various ranges of fines content represented by the base soil category. The no erosion filter design criteria for dispersive soils is more stringent, as shown at the right of the table. If a filter fails the no erosion screening, then evaluate the other erosion boundaries using Foster and Fell 2001 to assess how much erosion is required for self-filtering to occur and whether it can be tolerated. For the continuing erosion condition, the filter is too coarse to allow eroded base materials to seal the filter, allowing unrestricted erosion of the base soil. Thus, this condition and the no erosion condition are the bounds for filter performance. As mentioned previously, the effective pore diameter of the filter, i.e. the maximum diameter of pores that will allow soil particles to pass, is equal to about the D15 of the filter divided by 9. The D95 of the base is compared against this opening size for the continuing erosion boundary. The excessive erosion and some erosion boundaries were estimated based on a comparison of laboratory filter tests to case history data of pore filter performance, which showed progressive sealing of the filter zone as shown in the figure on the right. The excessive erosion boundary occurs between the some erosion and continuing erosion boundaries, where erosion of base soil is excessive before it seals. Filters will eventually seal, but only after significant erosion of the base soil, and there may be large leakage flows before the filter seals by clogging of the filter by the eroded base soil. The some erosion boundary occurs between the no erosion and excessive erosion boundaries, where the filter quickly seals after particles of the base material clog the surface of the filter. This slide represents the criteria for the excessive erosion boundary. The equation of the D15 of the filter, approximately equal to 0.34 times 1.07 raised to the percentage of fine and medium sands, was obtained by USACE from a curve fit to the 0.25 grams per centimeter squared line in the CEF test. Make a note here that the range of fine to medium sand, or FM, is the percentage between 0.075 to 1.18 millimeters in this equation. This is different than the ASTM D2487, which defines fine to medium sand as a percentage between 0.075 millimeters and 2 millimeters. After estimating all 4 erosion boundaries, plot them on the original filter gradation curves on the D15 line as shown here. If the filter gradation must be adjusted to account for segregation or washout, then plot that curve as well. This figure zooms in on the D15 line from the previous figure so that erosion boundaries are easier to examine for estimating proportions. The suggested approach is to estimate the proportions for continuing, excessive, and some erosion first, and then calculate the proportion for the no erosion category by subtracting the sum of the other proportions from 1, thus making the erosion conditions collectively exhaustive. Fell et al. 2024 recommends making an initial estimate of the probabilities of no erosion, some erosion, excessive erosion, and continuing erosion by calculating the sum product of the fractions of the base soil gradation envelope and the estimated percentages of no erosion, some erosion, excessive erosion, and continuing erosion for the representative coarse, average, and fine base soil gradations. If segregation or washout is expected, this is done for the adjusted filter gradation curve in addition to the original filter gradation curve. Lastly, assess how representative the gradation may or may not be. Use judgment to adjust the calculated percentages to take into account the effects of other factors such as the distribution of the core and filter gradations in the fill, borrow area variability, and selective placement of materials. The probabilities should not be used directly in a risk assessment, but rather used to help develop a list of more and less likely factors during a team elicitation of probability estimates. Fell et al. 2024 suggested that each erosion category be carried through the event tree as shown. However, USACE makes a single estimate of the likelihood of an unfiltered exit because filter evaluation is just one aspect of continuation. The likelihood of continuation of erosion is based on not just the likelihood of the continuing erosion boundary being exceeded, but also considers the likelihood of excessive erosion, how far the material is from the no erosion boundary, the variability of the gradations from the fine to coarse extremes, the thickness of the filtering unit, upstream to downstream continuity, and extension to a free or open face. Now we'll move into a discussion of additional considerations when assessing existing filters. In addition to the erosion boundaries for particle retention, other filter considerations include durability resulting in degradation due to weathering or breakdown of weaker particle shapes, cracking based on the fines content, the presence of plastic fines or cementation, as well as overcompaction resulting in brittle zones, segregation during storing, hauling, dumping, spreading, and compacting, and washout due to internal instability. Some of these occur during handling, placement, and compaction of the filter. Additional filter considerations include heave due to insufficient cover if the filter is the only material on the downstream embankment face, sufficient permeability of the filter in the downstream zones to perform their required drainage function, continuity to an open face or extensive void space in coarse soils or bedrock for eroded fine particles, and inadequate filter width. The likelihood that the filter will hold a crack can be estimated using the table on this slide, taking into account the fines content, plasticity of the fines, whether the filters were manufactured from natural sand and gravel or from crushed rock, degree of compaction of the filter, and crack width in the core and the filter. The descriptors and probabilities should be used to help develop a list of more and less likely factors during a team elicitation of probability estimates. Here are some factors influencing whether a filter will hold a crack and whether that crack will remain open. Filters with high fines content, plastic fines, or high coefficients of uniformity are more likely to hold a crack. Crushed rock filters are more likely to hold a crack than those that are manufactured from natural materials. Angular natural gravels may behave in a similar manner to crushed rock, and filters with a mix of both should be considered as crushed rock filters. Dense filters are more likely to hold a crack than loose filters, and wide cracks are more likely to remain open than narrow cracks. Finally, fine filters with carbonate rocks such as limestone, marble, or dolomite are more likely to hold a crack, and filters with small percentages of sulfide minerals may also result in cementation and the ability to hold a crack. Typical criteria to reduce cracking potential include limiting the fines content, the plasticity of the fines, and the compaction effort. To limit the in-place fines content to 5%, it's often necessary to limit the off-the-belt fines content to 3% at the quarry or crusher stockpile to account for breakdown during handling, transportation, placing, and compacting. Compaction of filters should be minimal. Very densely compacted sands can result in overly brittle zones that have less than desirable self-healing properties. Excessive compaction, particularly of crushed rock, can lead to the creation of sufficient fines in the filter to make them susceptible to cracking. Dynamic loading by the compactor is the critical component in compacting granular materials. Compaction of filter and drain materials should be adequate to produce sufficient density to preclude liquefaction, limit consolidation, and provide adequate strength. Minimum density should generally not be less than 70% relative density, particularly if liquefaction is a concern. Reclamation and USACE tested commonly used filter materials, moist concrete sand with less than 5% non-plastic fines, in single-stage and two-stage vertical chimney filter configurations. The densities at which the tested filter sands flowed freely and self-healed were very low, much lower than anticipated. In most, if not all cases, it would be difficult to consistently achieve this low of densities in the field, and if achieved, it may be impractical to ensure they remain at such low target density due to construction of and associated loading from adjacent and overlying fill. Inclusion of a second stage or gravel zone appears to provide a more practical solution to designing a chimney filter capable of healing and sealing a concentrated leak when subject to severe cracking than close control of density of a single-stage sand filter. Test results confirmed that the two-stage filters are very robust and retained functionality even when subjected to large cracks upstream and downstream of the chimney in the laboratory. In the lower right figure, the crack was sustained in dense concrete sand but not in gravel. The sand at the interface with the gravel is similar to the previous filter action slides. This slide illustrates how the generic event tree can be adapted if filter cracking is a concern. In this example, a node is added to assess the likelihood of common cause cracking in the Zone 2 or pervious shell due to excessive fines. If Zone 2 is cracked, an unfiltered exit exists in the next node, as shown in the upper branches. Otherwise, the continuation node assesses the particle retention capability in the complementary next node for the uncracked Zone 2. Segregation is the tendency of large particles in a given mass of aggregate to gather together whenever the material is being loaded, transported, or otherwise disturbed. Material placed in a pile off of a conveyor, loaded from a chute, or from a hopper segregates because the larger particles roll to the sides of the stockpiles within the hauling unit. Material dumped from a truck, front loader, or other placing equipment almost always segregates, with the severity of the segregation corresponding to the height of the drop, the moisture content, and the maximum size of the particles. Soils which are susceptible to internal instability are also susceptible to segregation. Segregation can cause pockets of coarse zones that may not be filter compatible with the material being protected. However, to be a significant contributor to the likelihood of continuation, an entire lift of the filter zone has to be segregated from upstream to downstream, which is very unlikely except for very narrow zones, and the segregated layer has to correspond with a flaw or concentrated leak in the embankment. This slide shows criteria to reduce the potential for segregation. The upper table provides minimum and maximum particle sizes for filters, and the bottom table provides the filter design criteria to limit the maximum allowable D90 of the filter based on the minimum D10 of the filter. When assessing an existing filter that may be prone to segregation, evaluate the susceptibility of the filter material to the geometric criteria of internal instability as described in the internal instability presentation using the RMC internal instability toolbox. This slide illustrates how the generic event tree can be adapted if the filter is susceptible to segregation or is internally unstable. In this example, a node was added to assess the likelihood of the filter being segregated or internally unstable. Given the filter is susceptible to segregation or internal instability, the next node assesses the likelihood of continuation based on the adjusted gradation as shown in the upper branches. Given that the filter is not susceptible to segregation or internal instability, the complementary next node assesses the likelihood of continuation for the stable filter and its unadjusted gradation as shown in the lower branches. The following table from the Best Practices Manual can be used to help assess the likelihood of continuation of internal erosion. It can be used as a starting point, but the risk team must develop project-specific more likely and less likely factors to guide subjective probability estimation. The factors in this portion of the table address embankment zoning, filter gradation, and cracking. This portion of the table addresses materials downstream of the filter location, the filter width, segregation during construction, and internal instability. The final portion of the table addresses gradation testing and tow drains. The last topic for discussion is constricted or non-erodible exits. Up until this point, the presentation has discussed assessing the particle retention capability of filters. The last exit condition is a constricted or non-erodible exit. For erosion to continue, the open joint, defect, or crack in conduits, walls, or rock needs to be sufficiently open to allow the surrounding soil particles to pass through it. There are no commonly adopted criteria for assessing the likelihood of continuation, although some have used design criteria for the perforation size for drain pipes. Effective opening size of defects can be used to assess whether internal erosion will continue. Poorly designed or inadequately filtered underdrains, toe drains, relief wells, or weep holes into which embankment or foundation materials can be eroded should be evaluated using similar opening size considerations where applicable. The joint opening size, or JOS, which will allow continuing erosion is between the D95 of the base of the soil based on the assumption that the crack width is equivalent to the filter opening size of the voids between the particles in a filter, and 3 times D95 of the base soil based on criteria developed for the opening of joints in rock into which cement grouts will penetrate and flow along the joint. A range of D95 of the base of the soil should be considered. Constrictions that are retaining soils and preventing erosion need to be continuous to some exit point. Bedrock joints or fractures need to be continuous to an open face and not covered by alluvium. If extensive void space exists in coarse soils or bedrock, an open exit may not be needed, but sufficient storage space for eroded fine particles must be available. It's also important to consider the flow direction and the likelihood of flow reversal. To wrap up the presentation, we'll briefly list the worksheets available for use in the RMC Filter Evaluation Continuation Toolbox to assist in the evaluation of existing filters. The first worksheet in the toolbox performs a particle size analysis of the base and filter gradations and determines if regrading of the base soil is necessary for the evaluation. The second worksheet evaluates the existing filter for particle retention based on the no erosion condition, and the third worksheet follows the Foster and Fell methodology to assess the existing filter when it does not satisfy the no erosion criterion. The fourth worksheet assesses the continuing erosion condition for constricted or non-erodible exits. Finally, the fifth worksheet assesses the existing filter with regard to permeability criteria from USACE, Reclamation, and NRCS. The following slide lists the primary references that were used to put together this presentation. This concludes the presentation on the continuation phase of internal erosion.